Okay, so again, we want to find the Fourier transform of f times g. Now we know, we know that the inverse Fourier transform of f hat times g hat is equal to the convolution of f and g, and so that's basically the same idea that we want to use here. Again, we just want to try to use this duality idea. Okay, so let's see if we can work through this. Okay, so we want to do, so the Fourier transform, how did I do this before? I think it was like this. Whoops. Hat of omega. This is equal to the integral from x equals minus infinity to positive infinity, f of x, g of x, e to the minus I w, or omega x, and we're integrating with respect to x. And then we can write this. Okay, I'm going to do something very similar to what I did before, and then let's compile it and look at it. Okay. What did I do wrong? Something here, I'm guessing. There we go. Okay, so the Fourier transform of f times g is equal to this. Okay, now again, if we think about omega as being like the first variable and x is the as the Fourier transform variable, then we can think about this as being the inverse Fourier transform of f times g evaluated at minus omega. Okay. So this, and that's not quite right. So let me write up here. Recall that the Fourier transform of f star g, whoops, this is equal to the square root of 2 pi. This is equal to the square root of 2 pi times the product. So like this. Or changing roles of variables. Okay, I'm just going to do the same thing. I'm going to do the same thing, but change the x's and the w's. Okay, so we've got an x here. I say w. Yeah, so that's going to be an x. I'm saying w, but of course I mean omega. Okay, so in other words, the inverse Fourier transform of f of x, g of x, the inverse Fourier transform of f of x, g of x. Okay, again, we're thinking about x as being the Fourier transform variable now. So the inverse Fourier transform of f of x, g of x is, I'm going to take this line right here, but divide both sides by the square root of 2 pi. So this is frac 1 then it's going to be the so this is the Fourier transform. We're doing the inverse Fourier transform, so it's just going to be the convolution f like this. Okay. Okay, so now, all right, so so there's a typo here. The inverse Fourier transform of f hat g hat. Sorry, the inverse Fourier transform of f hat times g hat. Okay, so let me run that. the inverse Fourier transform of f hat times g hat. Again, typically we would have omega. If we're talking about inverse Fourier transforms, you would have an omega there. Okay, but what we're saying is the inverse. We're thinking about swapping the roles of the x and omega. So the inverse Fourier transform of f hat of x times g hat of x is 1 over the square root of 2 pi times this convolution. Okay, so now we're going to do something that's similar to what we did before. If we just write this with check, like if we apply this with, instead of f, we have f check, and instead of g, we have g check. So we're going to have to get the following. Okay, so now if we apply this formula, but instead of having f hat and g hat, or sorry, instead of having f and g there and there and there, we'll have f check and g check. Applying this with actually, I don't want to do this. This gives that the inverse Fourier transform of, so if I'm thinking about there being an, so I'm just replacing that f with f check. So this is f check hat, which is just f, and this is g check hat, which is just g. So the inverse Fourier transform of f of x, g of x, is going to be equal to 1 this times check f check g of omega. Okay. Okay, so now we're going to come down here. The thing that we're computing right here, what is that? Well, that is the inverse Fourier transform of f times g evaluated at minus omega. So again, we're doing this thing where we're looking at the x variables as being the Fourier transform variable and the omega variable as being like the more fundamental variable. Need to have an equal sign right there. Whoops. Okay, and so this is going to be the inverse Fourier transform of f times g, which is f check star g check divided by the square root of 2 pi. The only difference is that we're evaluating it at minus omega instead of omega. So it's just going to be equal to this. And we're going to put a minus omega here. Okay, and we have that right there. Okay, so let's compute. Well, let's just compute what that convolution is. You know, by definition, this is 1 and then we're going to have the integral. Let's say we'll go from, I'm going to use the variable y to kind of stick with how we normally do things. Infinity to positive infinity. Whoops, not hat. Check f of, okay, so wherever we see the argument, we're going to put minus the argument. So it's going to be minus f of minus omega minus y. Hold on. Yeah, okay, so omega, I can never remember if it's y minus omega or omega, anyways. Okay, and then check g of y dy. Okay, so now what we can do here, we can switch to the Fourier transform. Okay, so this is going to be the integral y equals minus infinity to infinity. Sorry, I made a mistake. So notice it is a convolution applied at minus omega. So I was wrong. It's not wherever we see the argument we put minus omega. It's going to be minus omega minus y. Because this is a convolution evaluated at omega, we want the convolution evaluated at minus omega, so it's going to be like that. Okay. Okay, and so now let's see what we're going to do here. This is going to be Sorry, let me just double check that I have the formula here correct. It's embarrassing, but I always forget the way that the convolution goes. So the variable of integration goes second. Yeah, okay, that's the variable of integration. Okay, so now this is equal to hat f, and it's going to be the negation of this. So that's going to be omega plus y times hat g of minus y dy. Okay, now we can make a change of variables. Let me just write this out explicitly. Make the change of variables u is equal to omega plus y. So that, let's see, minus y, if I subtract y from both sides, I'm going to have minus y is equal to omega minus u. And this is, okay, I'll go ahead and put the left-hand side of the computation. That's what that is. And this, I'll probably do this in 2 lines. Okay, so I'm going to just do a little copy and pasting here. Okay, so u is equal to omega plus y. I'll change the limits in just a second, so that's going to be equal to u. And then if I subtract y from both sides, again, it's going to be minus y over there. If I subtract y and subtract u, it's going to be minus y over here and omega minus u. So minus y is omega minus u. So I'm going to have that. If I look at this, du is equal to dy, because d omega is just 0. So this is going to be a du here. And then my limits are going to go still from minus infinity to positive infinity, but we're going to have a u here instead. And then this is just exactly equal to this times f times the convolution of f and g evaluated in w. Sorry, not f and g, f hat and fg. Now, there's just like for the Fourier transform of x times f of x, there's kind of like more succinct ways to do this. I may be explaining it a little bit more just to try to get what's going on here correct, just so that we understand this sort of duality between the Fourier transform and the inverse Fourier transform. But another way to do this would be just to compute this and then do something very similar to what we did in class to find the Fourier transform of the convolution. So just do something very similar to what we did, sort of opposite though, in a certain sense, to find the Fourier transform of the convolution. You do something very similar, but like sort of start with this and work in the other direction, I guess. Okay, that's all that I want to have for this one.